which is Sabbagh, and it's going to talk about model reduction. Go ahead.
All right, so hello everyone, my name is Sabbagh, and I'll present my work with Dr. Dany and Jaoude on model reduction of consensus networks via selection of optimal edge weights and Nodal timescales. So dynamical network systems appear in various applications such as robotics, autonomous spacecraft, wind farm optimization, and multi-agent systems. And in particular, consensus networks are often used to model distributed information sharing protocols, whereby a network of agents agree on a common value of interest. And it is common to analyze multi-agent systems by utilizing a graph to represent the network structure over which their dynamics evolve, where the graph nodes would represent the agents and the graph edges would model the interconnections between them. However, as network systems increase in size and complexity, it becomes desirable to find smaller network models that approximate the behavior of the original network system. And so this work proposes H-infinity and H2-based model reduction methods to approximate the input-output behavior of a consensus network system based on a predefined clustering of its graph structure. So this work considers consensus network systems that consist of time-scaled single integrator agents evolving over simple, undirected, weighted, and connected graphs. So generally, the common approach in clustering-based model reduction techniques consists of finding a good clustering for the network system as a first step, followed by the application of the clustering-based projection to obtain the reduced network system as a second step. And so Cheng et al.'s work and our present work build on step 2 by parameterizing the reduced network system and tuning those parameters for improved results. For example, in 2019, Cheng et al. Constructed a more accurate reduced network system by tuning the graph's edge weights to minimize the H2 norm of the error system. And the method was extended in 2020 to account for directed graphs. And so our work extends the scope of Cheng et al.'s work in two ways. First, we consider consensus networks that are parameterized by both edge weights and nodal timescales. And second, we develop an H-infinity-based model reduction method to select these parameters in addition to the H2-based method. And our proposed H-infinity approaches are novel even when the edge weights are the only parameters considered for the reduced network system. So we now present the problem setup of the paper. So consider a consensus network system sigma consisting of time-scaled single integrator agents evolving over simple, undirected, weighted, and connected graph G, and define the following terms. E and W are positive definite diagonal matrices that contain the nodal timescales and edge weights of the consensus network. And the dynamics of the consensus network are given as follows, where X, U, and Y are the state input and output of the system, and L and D are the Laplacian incidence matrices of the system's graph structure G. So for example, consider a consensus network with the following graph structure. This graph has 10 unscaled nodes and 15 weighted interconnections. And a color coding of the nodes is given that partitions the node set V into 5 distinct clusters. And that's essentially going to be our predefined clustering of the graph structure. So this clustering of the graph can actually be characterized by a clustering matrix phi. And this matrix will be used to construct the reduced network system as follows. So nodes within the same cluster are combined into a single node, and the edges within the same cluster are removed. And if there's at least one edge between pairs of nodes in different clusters, then a single edge is retained in the reduced graph. Otherwise, no edge exists between the two clusters. And by doing this, a reduced simple undirected and connected graph G hat is obtained. And in our work, the matrices E hat and W hat are kept as parameters to be optimized, whereas as opposed to classical approaches where these matrices would also be constructed from the projection matrix and the original weights and timescales E and W. So as a result, we obtain the following reduced network system. The underlying graph has basically 5 time-scaled nodes and 5 weighted interconnections. So the dynamics of the original consensus network and the parameterized reduced consensus network are shown. And so the objective then is to tune E hat and W hat so that the approximation errors, which in this work are quantified by the H-infinity and H2 norm of the error system, sigma minus sigma hat, is minimized. The matrices F hat, H hat, and D hat are constructed based on the clustering matrix phi and so are fixed. And finally, alpha and beta are scalars that will be chosen to ensure that any set of reduced nodal timescales or edge weights yield a bounded input, bounded output stable error system, and thereby ensure that these reduction errors will always be bounded. So oftentimes, the Petrov-Galerkin projection paradigm is applied in clustering-based model reduction techniques after carefully choosing the clustering matrix phi. For example, the projection in the Petrov-Galerkin projection paradigm would result in fixed reduced nodal timescales and edge weights, set equal to the timescales and edge weights that were clustered together in the original system. Whereas in our work, the reduced edge weights and nodal timescales, they're parameterized and they will be tuned as shown in the bottom figure on the right. And so we can now formally address the problems in this paper. So given a consensus network sigma and the corresponding parameterized consensus network system sigma hat, solve the optimization problems shown, which consist of finding the reduced normal timescales and edge weights to minimize the H-infinity or H2 norms of the error system. And the works of Zhang et al. Basically consider the second problem with the reduced normal timescales fixed, as shown. So first, a realization of the error system, sigma minus sigma hat, is constructed. And since we're dealing with undirected and connected graphs, the state matrices of sigma and sigma hat each have a single zero eigenvalue, with the rest being negative real. And so this results in two zero eigenvalues in the state matrix of the error system. And thus, a condition on alpha and beta must be imposed to establish the BIBO stability of the error system. And specifically, it turns out that if alpha times beta is equal to the trace of E hat over the trace of E, then the error system is feasible for all possible choices of, is BIBO stable for all possible choices of reduced roll timescales and edge weights. And this condition on alpha and beta ensures BIBO stability by canceling the poles at the origin from the transfer function of the error system, which would guarantee bounded reduction errors. Furthermore, these reduction errors are invariant under specific choices of alpha and beta so long as their product satisfies the specified condition. And so in particular, we choose alpha equals to 1 and beta equals to the trace of E hat over the trace of E. So we're now ready to present our approach to solving the H-infinity model reduction problem. So the norm of the H-infinity norm of the error system can be characterized by a matrix inequality in W hat and E hat, as shown here. And this characterization will be used to develop an optimization algorithm to select the reduced parameters, whereby the H-infinity norm is reduced by minimizing gamma hat. And although in this characterization, the variables W hat and E hat are like decoupled from the remaining variables, and that psi infinity is linear in its arguments, phi infinity is highly nonlinear in its arguments, and so to handle this nonlinearity, we will alternate between optimizing the weights for fixed normal timescales and vice versa. So not simultaneously optimized. So for fixed timescales, the original problem reduces to the following optimization problem, where the constraint is no longer a function of the modal timescales. And in this case, the simplified inequality constraint takes the form of a difference of two convex, positive semi-definite convex mappings. And inequalities in this form can be readily dealt with by iteratively solving a linearized version of the optimization problem. So namely, the concave term can be linearized around the previous solution so that the inequality constraint function becomes convex. So in particular, to solve the problem for fixed timescales, the following algorithm is proposed, which iteratively solves the linearized optimization problem until the algorithm converges to a local solution. The linearized inequality constraint is more restrictive and therefore ensures that at every iteration, the original constraint of the problem is satisfied. And finally, it follows by lemma 1 that all pairs E hat and W hat are feasible starting points to the algorithm. Now for fixed edge weights, the original problem reduces to the following optimization problem, where the constraint is no longer a function of the edge weights this time. And while the weights optimization problem that we saw before was readily handled by iterative linearization, in this case, phi infinity is not concave in E hat. And in fact, more involved manipulations for the timescales optimization problem is required to be written in a form amenable to solution by the method previously discussed. And specifically, the structure of this inequality constraint function can be leveraged by doing two things. First, treating E hat inverse as the optimization variable instead of E hat. And second, introducing an additional matrix value variable Z set equal to E hat. And by performing these steps, the problem is reformulated as shown with the added equality constraint. And in fact, in this reformulation, phi infinity is concave in its arguments. And so the equality constraint function is now expressed in a form that can be handled by iterative linearization as previously discussed. However, there remains to deal with the added equality constraint Z equals E hat inverse inverse, which is not linear in the optimization variable E hat inverse. And so a remedy for this is to split the equality constraint into two inequality constraints, the first of which is converted into an LMI via the true complement formula. And the second inequality turns out to be yet another difference of two convex mappings. So all in all, to solve the problem for fixed edge weights, the following algorithm is proposed, which iteratively solves the linearized optimization problem shown on the slide until the algorithm converges to a local solution. As for the H2-based model reduction problem, a similar strategy can be followed based on an LMI characterization for the H2 norm of the error system, and analogous iterative algorithms are proposed. For example, for fixed edge weights, the following linearized optimization problem is solved iteratively in the timescales optimization algorithm in the H2 setting. Finally, all proposed algorithms in this paper can be initialized by the solution obtained from applying the Petrov-Galerkin projection framework. And this ensures that the results are at least as good as the ones obtained from this classical paradigm, as will be seen in the upcoming example. So we now revisit our example to demonstrate our proposed methods. So figures A and B show the underlying graphs of the original and reduced consensus network systems. And in the reduced system, the edge weights and nodal timescales are free parameters to be optimized using our proposed algorithms. And in this example, nodes 6 and 7 receive external inputs and are highlighted with an additional circle. And the difference between the values of the state variables of nodes 6 and 10 is measured in this example. So depending on whether we're optimizing the edge weights for fixed nodal timescales or vice versa, a different iterative algorithm is applied, such that a total of 4 algorithms are possible. They're numbered 1 to 4, and they're defined as shown. And algorithms 1 and 2 deal with the H-infinity optimization, whereas algorithms 3 and 4 deal with the H2 optimization. So the results are reported in the following tables. The first table compares the normalized H-infinity and H2 reduction errors of the Petrov-Galerkin projection framework to the ones obtained using our proposed algorithms. For example, algorithm A1 performs a tuning of the graph's edge weights to minimize the H-infinity norm, whereas algorithm A1 arrow A2 fixes this tuned edge weight matrix and then tunes the nodal timescales via algorithm 2. And it can be seen that a significant decrease in the reduction error is obtained when the nodal timescales are parameterized and tuned in addition to the edge weights. Sample resulting edge weights and timescales are shown in table 2. And at each iteration of the algorithm, the semi-definite programs were parsed using YALMIP and solved using MOSEC. And finally, it seems that in this example, tuning the edge weights after tuning the nodal timescales results in a small improvement in the reduction error. And it is of interest to conduct extensive simulations to verify this observation in other examples. So to conclude, we proposed H-infinity and H2-based model reduction methods for consensus network systems, where the reduced network is parameterized and its parameters are tuned via iterative algorithms. Compared to the Petrov-Galerkin projection paradigm and other existing works, our methods show improved results by additionally optimizing the nodal timescales of the reduced network. Our H-infinity-based approaches are novel for optimizing the edge weights, nodal timescales, or both sequentially. And finally, further investigation into simultaneously optimizing the weights and timescales and extensions to the work for directed graphs is of interest for future work. Thank you.
We have time for some questions.
So your network and your reduced network are both semi-stable systems, and then you have defined an error system that has error dynamics defined by an H2 or an H-infinity norm. Do you have conditions that exist to ensure that that's going to be bounded, that you're actually be able to produce those norms? Just like those need to share the same fixed point, or is there some other condition?
Yeah, that's a great question. So actually, the scope of this work deals with network systems that are bounded input, bounded output stable. So the only thing we need for this to work is for there to be no poles at the origin. So the original consensus network system, for example, would need to be bounded input, bounded output stable. But yeah, as long as the error system is bounded input, bounded output stable, the approximation methods are verified.
Can I ask one quick question?
Yeah.
Are you able to handle, like, if I want to add a weight and do frequency weighted H2 or H-infinity norm? Like in balanced truncation, you might add a frequency weight.
Yeah, I'm not sure how would this affect the because the characterizations used here are based on, for example, for the H-infinity, it's based on the bounded real lemma,
yeah.
And the H2, it's based on another similar LMI characterization. I'm not sure if with the frequency weighted norms, if that would change, or if something more complicated would need to be dealt with.
Cool, thanks. Any other questions? Maybe we could have the next speaker come up and change while we're